I have found a way to prove that Goldbach's conjecture is not true. We start by defining all prime numbers as either a multiple of 6 plus 1 or a multiple of 6 minus 1. Then the conjecture could be expressed in these three ways. 2n being any even number. In other words, any even number can be expressed as the sum of a multiple of 6 plus 1 plus a multiple of 6 plus 1, or a multiple of 6 plus 1 plus a multiple of 6 minus 1, or a multiple of 6 minus 1 plus a multiple of 6 minus 1. If we expand the first expression, we get the following. Now, 6a plus 6b will result in a multiple of 6, which we can call 6c, and replace it in the expression. Dividing everything by 2, we get. In other words, this expression holds true for all even numbers that are double a multiple of 3 plus 1. Doing the same with the second expression, we get dividing by 2. In other words, the second expression holds true for all even numbers that are double a multiple of 3. For the third expression, we get dividing by 2. This means that the third expression is true for all even numbers that are double a multiple of 3 minus 1. Now, we can agree that all integers in existence are either a multiple of 3, a multiple of 3 minus 1, or a multiple of 3 plus 1. Therefore, this proves that all even numbers can be expressed as the sum of two multiples of 6 plus 1 or two multiples of 6 minus 1. That being said, not all multiples of 6 plus 1 and multiples of 6 minus 1 are prime numbers, so this is not enough to prove the conjecture. If we list all multiples of 6 plus 1 and multiples of 6 minus 1 up to 66, we find that the following numbers are not prime: 25, 35, 49, 55, and 65. Although these numbers are not prime, they are the result of the multiplication of two prime numbers. We can break them down like this. From this, we can notice the following pattern. 25 is a multiple of 6 plus 1. 5 is a multiple of 6 minus 1. 49 is a multiple of 6 plus 1. 7 is a multiple of 6 plus 1. Therefore, a multiple of 6 plus 1 multiplied by a multiple of 6 plus 1 will result in a multiple of 6 plus 1. And a multiple of 6 minus 1 multiplied by a multiple of 6 minus 1 will also result in a multiple of 6 plus 1. On the other hand, 35 is a multiple of 6 minus 1. 5 is a multiple of 6 minus 1. 7 is a multiple of 6 plus 1. 65 is a multiple of 6 minus 1. 5 is a multiple of 6 minus 1. 13 is a multiple of 6 plus 1. This means that a multiple of 6 plus 1 multiplied by a multiple of 6 minus 1 will result in a multiple of 6 minus 1. And a multiple of 6 plus 1 multiplied by a multiple of 6 minus 1 will also result in a multiple of 6 minus 1. We can expand the first expression like this. The second expression can be developed like this. The third expression. Finally, the fourth expression. These four resulting expressions can be used to obtain all numbers that, if multiplied by 6 and added or subtracted 1, will result in numbers that are multiples of prime numbers. We can replace b and c with any integer in each expression to get a list of all such numbers. Doing this with all integer numbers, we get two different sequences of numbers, one for 6a plus 1 and the other for 6a minus 1. These two sequences provide a helpful insight into the distribution of prime numbers because all the numbers that are not included in the sequence will all result in prime numbers when multiplied by 6 and added or subtracted 1. To explore the implications of this, we can break down the sum of all multiples of 6 plus 1 and minus 1 for one even number, for example, 70. Listed here are all multiples of 6 plus 1 and minus 1 that are lower than 70. Since 70 is double a multiple of 3 minus 1, the only numbers that can be used to add 70 are those on the left, 6a minus 1. Hence 5 plus 65, 11 plus 59, 17 plus 53, 23 plus 47, 29 plus 41, and 35 by 2. Now, looking at the sorted list for 6a minus 1, we can see that only two of those numbers appear in the breakdown of 70. 6 and 11 which occupy positions 1 and 2 in that sorted list. This means that out of 11 numbers, only 2 will be discarded as not being prime numbers, 35 and 65, and the remaining 9 numbers can be paired together to add 70. The same can be done with all numbers in the sorted list. Each number minus the position it occupies will result in a remaining amount of prime numbers that can be paired together to express an even number as a sum of 2 primes. Now, since the numbers that are not prime can be paired with prime numbers to result in an even number, we must discard one prime number for each non-prime number. So, in order to prove the Goldbach conjecture, the amount of prime numbers under any even number must be at least 2/3 of all multiples of 6 plus 1 and minus 1, so that we have a remainder of prime numbers after discarding all non-primes. Looking at the full sorted list, we see that this pattern persists until position 49 of 6a plus 1 and position 101 of 6a minus 1. All the positions after these keep growing in favor of non-primes, thus making it increasingly difficult to discard all non-primes to find pairs of prime numbers that can be used to sum an even number. This seems to indicate that Goldbach's conjecture is actually not true, since the necessary condition to prove it does not persist with the linear progression of numbers. So, then we can ask, what is the necessary condition to prove that Goldbach's conjecture is not true? Obviously, we would need to find a number that cannot be expressed as a sum of 2 primes. But what exactly would that imply? To answer that question, let's look at the breakdown of multiples of 6 plus 1 and minus 1 for another number, 122. This time we have crossed out all non-prime numbers on the list. Since 122 is double a multiple of 3 plus 1, we look at the numbers on the right, and we find a very specific pattern. 13 of those numbers are prime, and 7 are not prime, and they all occupy a unique set of positions in the sequence. As we observe with 70, each number in the sequence gets paired with a number in the opposite position to sum the current number. Thus, the first gets paired with the last, the second with the second from the bottom, and so on. The last line is not counted in this case. Now, if Goldbach's conjecture was not true, all the prime numbers in the sequence would get paired with non-prime numbers, thus discarding all possible pairs of prime numbers. In other words, the position of each prime number in the top half of the sequence would need to be mirrored by non-prime numbers in the bottom half. In this case, we are talking about a coincidence of 10 to 10, which happens to be absent in the example. As a matter of fact, as the number increases, the complexity of the sequence would increase as well, thus making it increasingly difficult to find a matching pattern on the opposite side of the sequence. This is the reason why Goldbach's conjecture keeps proving true for all even numbers that have been verified so far. However, as we observed before, all multiples of 6 plus 1 and minus 1 keep growing in favor of non-primes as we progress through higher and higher numbers. So the proportion of non-primes to primes becomes larger and larger, potentially bridging the statistical gap that impedes non-primes from mirroring every single prime position under every even number. So, how large would the proportion of non-primes to primes need to be in order to bridge the gap? Right now, it looks like that question can only be answered through brute force attempts at finding exceptions for the conjecture, but we can make estimates based on suggested values. For example, we can claim the proportion of non-primes to primes needs to be 100 to 1 in order for each prime number position to be mirrored by non-primes. How large would a number need to be to reach this proportion? Let's look at how the proportion increases for known numbers. Under 100, there are 32 multiples of 6 plus 1 and minus 1, 23 of which are prime numbers and 9 are not, so the proportion is approximately 0.3. Under 1,000, there are 332 multiples of 6 plus 1 and minus 1, 166 of which are prime, and 166 are not primes, resulting in a proportion of 1. Under 10,000, there are 3,332 multiples of 6 plus 1 and minus 1, 1,229 of which are prime numbers, and 2,103 are not prime. Thus, the proportion is approximately 1.7. Under 100,000, there are 33,332 multiples of 6 plus 1 and minus 1, of which 9,592 are prime numbers and 23,740 are not. So the proportion is approximately 2.4. We can already identify a pattern from these values. As we increase a number by 10, the proportion of non-primes to primes increases by approximately 0.7. If we assume this increase in the proportion is maintained as we keep increasing the number, then we would need to increase it by 10 about 68 more times in order to reach a proportion of 100. In other words, we're talking about 1 times 10 to the 73. That's how large a number might need to get to break the Goldbach conjecture. If we decide to aim for a proportion of 1,000, then the number would need to get as high as 1 times 10 to the 703. We're talking about numbers that vastly exceed our current computational capabilities, thus making it impossible to disprove Goldbach's conjecture for the time being. In conclusion, we can claim that we have identified the necessary condition for Goldbach's conjecture to be true, and we have proven that this condition does not persist with the linear progression of numbers. However, due to the complexity of the patterns created by the positions of prime numbers, the conjecture keeps proving true for all numbers we have checked so far, and it would require an astronomical increase in our computational capabilities to find an even number that does not match the conjecture.